Okay, so what I'm going to do is finish the article that we have up here, and then I'll probably do a couple demonstrations if you have time, and then we'll we'll get to the study guide and study for the test. How about that? All right. This is where we left off, and it says here that we talked about the different kinds of flames, or the diffusion-fed flame. And what does that mean? Diffusion-fed flame. What do you? How fast can it burn? How fast can that fire burn? And it can only burn as fast as oxygen can diffuse into that area, right? Well, that's what a candle is. It's a diffusion fed. So, but at home, if I have a gas stove, if I turn the gas on a little bit, I get a little bit of fire. If I turn it on higher, I get more fire, because that's a pre-mixed flame, and they actually mixed the right amount of oxygen with the fuel, so you don't have to worry about waiting until the oxygen gets there, like that. Okay. All right, then they talked about the different zones, and I do have a thing on the test where you actually, it tells you what are the temperatures, point out what are the different temperatures on the flame. Have we done that yet? And then also, what's the name of them? There are 3 distinct regions of the flame. Now, if you look up here, and that's what this is all about, if you want to look in there, they talk about the different regions of there, and what do you remember about the dark zone? What is it that makes it so dark? Does anybody know what's in the dark zone? What's actually found in the dark zone?
Isn't that like a carbon that's not hot enough to burn?
Not yet. I actually did a demonstration where, you remember how I took the eyedropper and took some stuff out of the dark zone and pushed it back into the flame? What happened? I did that, remember that? Okay, so what happened when you take some stuff from the dark zone and push it back into the flame? What was it? It's like a flamethrower, wasn't it? So what's in the dark zone is fuel. And what is the fuel for the candle? What is it? What's the fuel? Paraffin. Not solid wax, not liquid wax, vaporized wax, right? Anyway, vaporized wax goes up, doesn't it? It's less dense than the air around it, so it goes up. And so it is up there, but it says in there, the dark zone is so dark because why isn't the fuel being ignited in that area? What's it say? Yeah, there's not enough oxygen, is there? There's not enough oxygen in there. And so if you have almost nobody burning, you get almost no light coming from that zone. That's why it's called the dark zone. And then we get to the luminous zone, the yellow part. And here, they said it's actually quite complicated what's going on. They said there's some parts of the flame they still don't understand. They still don't understand everything. It gets kind of complicated. And this right here, this zone here, the reaction zone, the blue zone, they're talking about all kinds of things happening there. And but there is a lot of oxygen. There's a lot of oxygen, so it's kind of more blue. So what is it that makes the flame yellow to begin with? And I thought I did. Did I do a demonstration where I tried to make a shadow up here? Okay. If I would have had a brighter light, I think I could have made a better shadow. A real bright light shining into a flame will make a shadow where the dark zone, or where the luminous zone is. And the luminous zone, it contains, what you said, a lot of carbon particles. So, and it's getting hotter and hotter. And so what happens to these carbon particles that you call soot? What happens to carbon particles when they get really, really hot? What's that fancy word that means they're so hot they're going to give off light? What was that fancy science word? I keep looking at your faces, half your faces. What is it? Incandesce. It incandesces, doesn't it? It actually glows. It incandesces. Believe it or not, that's why you see the flame. You see the flame because bits of carbon are glowing. Now, if you had plenty of oxygen in that zone, you would not see the flame. If we could pump a lot of oxygen into that yellow zone real quickly, the yellow color would go away. You'd have nothing being incandescing. It would all be changing into carbon dioxide. and water. Get that? Now remember when he talked about there were two kinds of combustion. Remember there was complete and incomplete. If you get complete combustion, you only get two products, carbon dioxide and water. But most of the time in the flame, it's incomplete. So what happens? You get carbon dioxide and water. And what other two things do you get with incomplete combustion? Carbon monoxide. That's true. What else? And it's why you see the candle flame. You get soot or carbon. Okay. Now that kind of finishes the story of the candle. I did want to do a couple of things, and then I'll leave that. This right here, I'll go ahead and do that for you. It's going to be difficult for them to see on the camera. See, if I put it back here, you won't see it. If I put, well, I'm just going to do it this way here. Did anybody in this class do this? I thought there was one class where somebody said they looked on YouTube, and did anybody do this one? Yeah. Okay. So what I'm gonna do? Take my candle. So I have the clay on it. There. Okay. Okay, so I light the candle, let it go for a little bit. Okay, there you go. On this page here, it says, a common demonstration involving the burning of a candle, and this is why it's on YouTube, because it's kind of neat. You didn't do this one? Yeah, okay, you did that, right? Okay, I have to give you a lot of credit for that. You actually looked up something. It's a neat experiment, and I think there was only one other person in the other two classes, and you're only two people total did this thing. A common demonstration involving the burning of a candle has occasionally been interpreted wrongly. Fix a candle at the bottom of a pan and with a bit of hot wax or clay. Pour water in the pan to a depth of blah, blah, doesn't matter. Light the candle and put a large clear jar over it upside down. The mouth of the jar should be submerged but held under the bottom. Okay, that's what I'm going to do. And so it's been explained the wrong way many, many times. So I'm going to try to explain it the right way. Can everybody see this? Are you in a position where you can see the candle? Okay. Remember I told you about observations are very powerful in science? Observe, ready? And go. All right, do you see what happened? Okay, so what happened there? Don't fall. This has been explained wrong, and he even says here, people try to say, well, the flame used up the oxygen and create a vacuum, and that sucked the water up. And that's what people say. But there was an observation that was very critical there. When I first put the flask on there, what did you see happen? You saw it, huh? Ooh, that's what I was afraid of. Ooh, the right went this way, not that way. What happened? Bubbles. That's important. See, what happened is when I put that in there, the heat from the candle, it heated up that air. And the air says, whoa, and it tries to expand. And as it expands, it tries to go through the water, go bubble, bubble, bubble. A lot of air actually leaves the flask. It leaves it. And then the flame goes out, and then that really hot air cools off. But the other air can't get back in to equalize it, and so you get a little bit of a vacuum there. And then, so this atmospheric pressure here pushes the water up into that empty space. So that's what this article was here. It says the effects have sometimes been erroneously attributed to the loss of oxygen. Until I read this about 30 years ago, I had explained it that way. I even had another chemistry teacher that they did this experiment, tried to prove the air was only about 20% oxygen, but between how much volume of water came in there. And yet that's wrong, because this guy says the amount of oxygen used up, the volume of oxygen used up, guess what else was given off by the flame? Yeah, I gobbled up oxygen from the air, but guess what I gave off? Carbon dioxide. And he says those volumes are almost identical. So that could not be the reason why a vacuum was created. What really created is the air got heated and a lot of air left. A lot of the air left. And then when it cooled off, this air here cooled off and contracted and made a vacuum like that. So that's what they were talking about, real famous. And you got that off of, was it YouTube? Did they explain to it how it did it? They just said, here's what you do. How do you know about this?
I just saw this app called TikTok.
Okay, all right. So did they actually explain anything, or just said, here's what you do and it's fun?
Yeah.
Okay. All right, sometimes they do that. All right. And the other thing, I think there's only one more. That's about it. That's probably about it, I think. Okay, what do you think? Now, you're going to have a chance at the end of the period to write the whole story. How does a candle work scientifically? But before we do that, let's go ahead and study for the test here. What I'm not certain about is, even though I graded these right after you gave it to me, it's very possible that it's sitting here. That's the wrong other class. It's this class. All right, now since you helped me before, I'll let you guys help me on this one. So, part of the test, and I told you this a long time ago, this is the only test all year where it actually involves a little bit of this, a little bit of this, a little bit of this. From now on, my chapter 2 is just chapter 2 in the handout sheets. So here's what we have. Look on the study guide, and it says that the first 10 questions are going to be from chapter 1. So it won't take you that long to go back and look at your notes and look at chapter 1. Now I'm going to focus mainly on the vocabulary words. Focus mainly on the vocabulary words for chapter 1, and some of them are like hypothesis, remember that? The scientific method. Remember how they had scientific theory, scientific law, remember that? So that's where you look at chapter 1 stuff. So chapter 1, here we go, has to do with what is chemistry. And we kind of said, well, it's kind of the study of matter and the changes in matter. And then we even had a little discussion about what CFCs were. Remember chlorofluorocarbons and how it protects the ozone layer, destroying the ozone layer, I'm sorry. Anyway, that's some stuff that we talked about with chapter 1. And then we had the scientific method. That led us into having you guys look for changes. Are changes physical changes, or are they chemical changes? And so let's go over some of those, ready? A chemical change, burning. Why is burning always a chemical change? Yes. Say it again. Well, one thing, I like what you said there. You mean it can't be reversed? There actually are some chemical changes that can be reversed. Like every night when you plug in your phone, what you're doing is there was a chemical reaction that made electricity during the day. And at night, you're asking that reaction to go backwards to recharge your battery. You know that? So there are reactions that can, but they both were chemical changes. Yes?
Well, burning's always chemical change because it creates like a completely new product.
Excellent. Now, if burning means you chemically combine with oxygen, you would have to make a new product, wouldn't you? So burning's always a chemical change, isn't it? What about heating? I'm going to heat some water. What kind of change is that? It's physical. It's still H2O. H2O. What if I boil some water? H2O. What's steam made out of? H2O. It's still physical. What if I freeze some water? So anytime it goes from solid, liquid to gas, or vice versa, it's going to be a physical change, isn't it? There's no new chemical there. Next, it says here physical changes. All phase changes are physical, and it gives some examples here. How about the Alka-Seltzer lab? I tried to do a demonstration to show you what the bubbles are made of. What were the bubbles made of? And I had, it was one day where I did a series of demonstrations. I said, what do you think they're made of? And they actually put out a flame. That's number one. What do you think they were? What were the bubbles from Alka-Seltzer? It's right here. I'm just going over this. The bubbles formed are what? Carbon dioxide. Because then I had a person come up with a straw, and I asked them to blow into some water. Remember that? Remember that? Now, that would have been a very boring demonstration, except we used this group of chemicals. What do you call that group of chemicals that actually change colors and let me know that something's going on? Indicators. Remember that? And BTB is an indicator, isn't it? And so I had somebody blow into some blue BTB water, and it went from blue to green or sometimes yellow. What did that tell you? Go down here where it says indicators. What does it mean when BTB changes? BTB can be blue, green, or yellow. So which one? What happened? What if I put Alka-Seltzer in BTB water? What happened? I need everybody to speak up so I can hear you real well, because I'm trying to review real quickly. If I put BTB in water and with Alka-Seltzer, what happened to the BTB? It went to yellow. Why? What is it about the carbon dioxide? And the person that blew in the water, the same thing happened. You blew carbon dioxide in the water, and you formed what? When does BTB change yellow? Acid, base, or neutral? Acid. You must be making an acid. What was that acid that makes when carbon dioxide combines with water, whether you breathe it in or the carbon dioxide from Alka-Seltzer, what was the acid? I think I have it on there somewhere. Is it written on there somewhere? Yeah, there it is. Carbonic acid. See right here? Okay. All right. So BTB, we know if it's in an acid, it's yellow. If it's neutral, it's going to be green. And if it's in a base, it's going to be blue. Okay, what's another indicator we used? Litmus paper. Remember litmus paper? Okay, so litmus can only do, either if you're blue, you stay blue, or you can turn red. Is that correct? Okay, so what color is blue litmus if it's neutral? Blue. What about red litmus when it's neutral? Red. Okay, so they're not going to change, right? Now, how do I remember which one's which? Do I have the little thing here or not? Oh, it is. Memory trick. Blue to red, acid. Is that right? So if blue litmus paper changes to red, I know I have an acid, don't I? So what's the opposite of that? Red changes to blue, must have been a base, right? Are you okay with this? I'm looking. Your face tells me what's going on, sort of, unless you fool me. All right? Madeline's trying to fool me, are you? Yeah. Okay, good. Okay. All right, so then there was another indicator which could seem like almost 10 colors. How is that? What was that called? And that was pH paper, but in liquid form it's called universal indicator. Now, why was it able to change so many colors? Was it just one indicator? It was several, like at least 4. There's at least 4 or 5 in there if you look at the ingredients on there. And so that's why I could change so many colors. What I think is interesting is one of the indicators would only change from like 1 to 2 or 1 to 3. Another one only changed from 3 to 5. See that? They had to pick the right ones so they could go all the way from pH of 1, maybe all the way to pH of 12. What's the pH scale? What are you measuring? Acidity, okay, or alkalinity. Alkalinity has to do with base. Acidity has to do with acids. And the pH scale goes from 0 to 14. What number says I'm not an acid or a base? 7. And what are the acid numbers? Are they the low numbers or the high numbers? And the memory trick was the letter A comes before B. Your acid numbers are your low pH numbers. Your base numbers are high, right? All right. Now, I know I'm going kind of quickly. I'm trying to cover all the stuff here. Got that? But you can take your time. Now we go over here, and I'm going to skip that just for a minute because I want you to do this at the end of the period, and you're going to get in a group of people and try to see if you can tell the story of the candle using all those words. Let's get down to here, okay? All right, what do you know about the temperature zones of the candle? Let me see if I can find a picture here. What do you know about the temperature zones? And I'll see if I can find it here. What is it? Yeah. If you remember, the top of the wick is around 600, right? And then you go right above the wick, how much is it? 800. Go to the top of the dark zone, it's about 1,000. And you go higher than that, it's about 1,200. So that one goes by 200s, right? But then you have to remember, where is the hottest part of the flame? It's actually not here. It's in this blue zone, isn't it? Now, if this is where the blue zone starts, it gets even hotter. So near the top of the blue zone is going to be around 1,400 degrees Celsius. Okay, what do you call the yellow part of the flame? The luminous zone. That's where most of the light comes from. What about the darkest part of the flame? Dark zone. And what about the blue part? And again, if you read that article, it said there's a lot of stuff that happens in the reaction zone that we're not exactly sure of all the chemistry that's going on there. It's some pretty complicated stuff that's going on in the reaction zone. Okay, let's go over here now. So they talk about the different zones here, reaction zone and luminous zone, and then dark zone down here. And do you remember the difference between complete and incomplete combustion? If I have plenty of oxygen, I'm going to get what they call complete combustion. What's the difference between combustion and burning? Yeah.
Combustion is like a fire, and then burning is just something is being pushed with oxygen.
It might look like a fire, though. You're right. So in chemistry, burning means you're going to chemically combine with oxygen. And I can burn it slowly. I can burn it quickly, right? I might get a fire. What did I just do with my lunch? What's happening to my lunch right now? It's being broken apart in my stomach. It gets in the intestines. And eventually, different molecules like glucose will get into my cell. And what's going to happen to those fuel molecules when they get into my cell? They're going to be burned. Now, God is pretty smart. He says, I better not burn that fuel very quickly. If I burn it quickly, it'll kill every cell that I created. So what did he do? You learned last year? He said, I'm going to burn the fuel in a series of steps. What do they call that? Cellular... Remember last year? Cellular respiration. What? That's that thing I had to memorize? Yeah. Remember the Krebs cycle? That's what that was. God says, I'm going to burn that fuel, but I'm not going to burn it like paper. That'll kill the cells. I'm going to burn it and release energy a little bit at a time. And as a matter of fact, a lot of the energy that's released, I'm going to retrap it and make some ATPs. That's how that story goes? Yeah, I'm going to make some ATPs and you can use it later for energy. Oh, okay, get it? But essentially, I wanted to burn that piece of glucose, and guess what was produced? If I had enough oxygen, what was produced? Carbon dioxide and water. Oh, man. This is kind of making sense now. Maybe. Okay, and then incomplete combustion, that actually takes place pretty often. Even an automobile, is not great at burning fuel. We know that because you can kill yourself. I hope you don't. But somebody, you could get killed accidentally if you run in your car into a garage with the door shut. Again, you won't know it. It's carbon monoxide. It doesn't smell like anything. It just makes you kind of tired. And you just kind of lay down and say, I'm really tired. And if you stay in that garage, you're going to die. So anyway, we know that even the automobile has incomplete combustion. The candle does too, but I was okay. It's just a little bit of carbon monoxide, and we had the doors open and stuff like that. So we were okay. We weren't going to hurt anybody burning a candle. And people have been burning candles for a long time, haven't they? So we're okay. Nobody's getting poisoned, carbon monoxide poisoned by our candles. All right, now let's go to the next one. I did some demonstrations talking about Michael Faraday. Let's see how much you remember about that. Michael Faraday says here, about when? What do you think? What time are we talking about? When did he do these experiments? He actually had done them, and then he gave them to the, remember the Christmas lectures he did? Okay, so what time period are we talking about? And what I would do on a test is I might give you a choice, 1560, 1760, 1860, 1960, 2006, no. Wait, what do you think? Which one would you guess? What is it? 1660? What do you think? Is that good? 17? 18? Okay. About 18. What's some other discoveries? He did some other discoveries, and one of the things that I think changed the world is discovery that there was a connection between blank, and it led to the invention of blank. So let's see if we can fill in these blanks. There was a connection between what? Magnetism and electricity. And what he did with that, it led to the invention of something where moving wires through a blank field will create blank. What is this about? What did he invent where you take moving wires and you move them through a what kind of field? Magnetic field. And what are you producing? Electricity. And what do you call something where I move the wires and it produces electricity for me, and everybody in the whole world uses this invention? What is it? One more time. Not yet, because the motor is where I give the thing electricity. This one's where I give it mechanical energy and produce electricity. What's that called? Somebody said it. A generator. All this electricity we see right now, Duke Power, that's what they have, generators. And what is a generator? It's a bunch of wires and magnets, isn't it? Now, let's go to the opposite. What if I provided the electricity and I got out of that a turning or some kind of motion, mechanical energy, then you'd call it a what? Caroline, since you said it before. A motor, electric motor, right? Is that right? And by the way, those are called motors, and the thing in your car is actually called an engine, but people like to call them motors, don't they? Okay, anyway, that's right. Okay, let's go on down here. I gave it away. And the invention of blank, where blank flowing through the blank can create a blank energy. Okay, so what's the second thing that led to the electric motor, where what? What do you do with electric motor? You let what? Yeah, let electricity flow through the wires, and that'll create a magnetic field, which will eventually give you movement, and that's mechanical energy. Okay. So, maybe I didn't word that very well. The electric motor, where electricity flowing through wires, well, they're actually flowing through wires, but that creates a magnetic field, and what you're doing is creating a mechanical energy, mechanical energy there. I don't think I worded that very well. Okay. All right. Now, if you were to go home tonight and say, well, I got to stay for this test, think about it. Spend a little bit of time with chapter 1 and say, I think I've got those words down, you know? I've got those words down, and I can get those. And then think about chemical and physical changes. Think about the indicators. We only had 3, and one of them's universal indicator, and that's really can be many colors, so it's hard for me to ask you questions about what color there. And then we had the Faraday's experiment, and then we had the candle. Now, what I'd like you to do is, for the rest of the time, you can sit at one of these tables, and you'll still be social, what do they call it? Distance, right? Socially distant. If you can sit at the table, like maybe at the 4 corners of the table, or you sit 2 on one side, 1 on the other. And here's what I'd like you to do. See these words here? I want you to try to use all those words in a story, and I actually started it for you. Now, if you want to write it out, it's up to you. If you have to write it out tomorrow, you won't have a partner. So you'll be writing it by yourself. But right now, you can have your buddies and say, I need help. I need help. How do we write this story? And just have somebody keep track of the words and said, we use it. We use that word. We use that word. Okay? All right, so go find somebody you don't mind sitting with, and even if you do mind sitting with them, sit with them anyway. That's enough for the day.